So welcome back, everybody. I think this is video number 7. So this one is going to be on our second to last gas law, Dalton's law of partial pressure. We're going to start this video with a warm-up from last week's gas law, the ideal gas law. So I'm going to take a minute and see what you remember. I'll read through it, give you a hint, and then you can pause the video and try to answer the question. 1.09 grams of hydrogen is contained in a 2-liter container at 20 degrees Celsius. What is the pressure in this container in ATMs? So the clue is you're going to use last week's gas law, the ideal gas law, PV equals nRT. So take a second and pause the video. I'm going to run through it. All right. So, remember what I like to do is underline my variables. 1.09 grams of hydrogen is not a variable in PV equals nRT, but it is used to get the variable N, moles. 2 liters is volume. 20 degrees Celsius is temperature, but remember that temperature needs to always be converted to Kelvin. What is the pressure in ATM? So I'm looking for P. So I list my variables. Remember, I'm turning N to moles. My volume is 2 liters. My temperature is 20 degrees Celsius. I add 273 to that to get 293. And I am looking for pressure. PV equals nRT. I divide by V to get P. I plug all of those numbers in, and I get a pressure in ATMs of 6.49. Remember, because your pressure is in atmospheres, you need to use the proper R, 0.08206. All right, so hopefully that makes sense. Last week's gas law, PV equals nRT. This week, we're going to move on from ideal gases and focus on mixtures of gases. And when you are done with this video, you should understand Dalton's law of partial pressure and use it to solve different problems. So, what does Dalton's law of partial pressure deal with? Well, it deals with a mixture of gases. Now, so far the problems we've been looking at have been with pure oxygen, pure nitrogen, pure anything. But in real life, you don't have a pure gas, typically. The air around me, the air around you, okay, is a mixture of gases. If I turn on my gas stove, it's going to change that mixture a little bit, okay, and you might smell it, okay, if you see that you hear that gas or smell that gas coming out of the oven, okay. These mixtures, okay, contain different gases, but how is their pressure affected once they become a mixture? That's what we're studying today. And experts have found, or studies have found, that gases behave independently if they're by themselves or with a mixture. So the pressure of an individual gas doesn't matter if it's by itself or in a mixture. Okay? For example, when would this come into play in real life? Here I have a reaction that is producing gaseous oxygen. Okay, so this reaction is taking place and producing gaseous oxygen. So this is allowing me to capture oxygen. But I need to understand this isn't pure oxygen. Why? Because I'm trapping it over water. Now, if I want to trap a gas, this is my typical setup. I have some reaction producing a gas. That gas would, if I just didn't have a lid on this container, it would just evaporate or leave the container and mix with all the gases around me into the surroundings. But because I have this lid on it, I'm forcing the gas in that tube, and I'm pushing it up into this bottle of water. This bottle of water began as a full bottle of water, but this gas is pushing that water out of the bottom. Okay? So the gas is replacing the water in the bottle. So I'm trapping oxygen gas here. And this is typically how you capture a pure gas. But again, I shouldn't say pure because it's not. There's the water cycle happening here. Some water is evaporating, some water is condensing. So in this mixture, there's also some water. So when I'm doing studies on that oxygen, when I'm determining the pressure of that oxygen, I need to take into account the other gases that are with it, in this case, water. So for this, I use Dalton's law of partial pressure. Remember John Dalton back from Unit 1 or 2? We studied his atomic theory, and he was kind of one of those early scientists in our current understanding of the atom. Okay, he had a big, deep part in that in Dalton's atomic theory. He also had a big part in gas laws. And he found that the sum of partial pressures of all different gases in a mixture is equal to the total pressure of the mixture. What does this mean? I'm going to use an analogy. Okay, so say I have crazy kindergartners, and I always compare kindergartners to gases because they're kind of the same. They move around chaotically. If you walk into a kindergarten or walk outside during kindergarten recess, they're just running around chaotically. It doesn't seem like there's a specific pattern. They're just flying all over the place. Okay, they're flying, bouncing off of walls, flying all over the place. Okay, so if I have kindergartner 1, okay, and we put kindergartner 1 into a room. He is kind of calm. He only bounces off a room or off of a wall once an hour, and that causes pressure. Okay. Then I have kindergartner 2. He has digested a little more sugar, he's a little more excited. He bounces off of 2 walls in an hour. Okay. So individually, this kindergartner bounces off of 1 wall an hour. He's running around, he hits a wall once an hour on average. This kindergartner on average bounces off and hits 2 walls an hour. He's moving a little faster, a little more chaotically. What if I put them both in the same room? What if I put them both in the same room? Well, it's been found that it doesn't matter. This kindergartner's still going to bounce off 1 wall an hour. And this kindergartner's still going to bounce off 2 walls an hour. So the total collisions here would be 3. It's an addition of this and this. So Dalton found that it doesn't matter if I have the gas by itself or in a group. The pressure that that gas exerts at a specific temperature in a specific area is not going to change. So I can get the total pressure of a mixture by adding up the partial pressures of those gases. It's a little easier gas law than what we've been doing because it's not really algebra here. We're just adding and subtracting. Okay? So if I have gas 1 in container 1, it has this pressure. I have gas 2 in container 2, same volume, it has this pressure. What if I put them in both in the same size container? Well, the pressure is going to be the individual pressures of these two. It doesn't matter that they're together now. The total pressure is simply the addition of the individual components. So what does this have to do with everyday life? Well, air is a mixture of gases. Okay, so how do I get that total pressure at sea level, 101.3 kilopascals, or 1 atmosphere? Well, it's because of the individual components in it. It's because 20.9 kilopascals is from oxygen. This is from nitrogen. This is from argon. This is from hydrogen or water, and this is from carbon dioxide. And there's other trace gases that make up air. But those individual components tell me the amount of each gas that I have in my total pressure. So about 20% of the oxygen or the air we breathe is oxygen. Most of it, between 75 and 80, is nitrogen. And then 1% is argon and water, and then trace gases after that. Okay. Now we use it in the science lab or the chemistry lab when we're trapping a gas over water. So here I produce this gas. Here's that reaction that I did earlier. Okay. I produce oxygen. But when I trap that oxygen, the total pressure in this jar, remember, is from both the water and the oxygen. So how do I get the pressure of just the oxygen? Well, I need to subtract from the total my pressure of water. Well, how do I get the pressure of water? Well, scientists have studied water. And what happens to the pressure when I heat water up? Well, that's like saying, does there more gas if I heat up liquid water? Is more water going to evaporate? And the answer is yes. And they've graphed this, collected data on it, and put it into a table that you can simply look up. So I can look up the partial pressure of water at specific temperatures, and no surprise it goes up. Okay? So if I have a temperature of that water is 20 degrees Celsius, I can look up the pressure, the partial pressure of water, and back on my problem here, okay, I can look up this value. I can look up the partial pressure of water at a specific temperature, and then if I determine the total pressure in this container, I can determine the partial pressure of oxygen that I have in that container. Also figure out from that, using the ideal gas law, how many moles of oxygen I have. Okay? So it's going to be useful when I'm dealing with mixtures of gases, which is most of the time. So we're going to do a few examples before we jump into our homework problems, which will deal with this gas law. So example number 1. A container holds 3 gases, oxygen, carbon dioxide, and helium. The partial pressures of the 3 gases are 2 atmospheres, 3 atmospheres, and 4 atmospheres. What is the total pressure? Hopefully we know. Remember, the total pressure is simply the partial pressures added up. So I take 2 plus 3 plus 4 and 9. Okay, pretty simple. All right, let's look at another one. Container holds helium, oxygen, carbon monoxide. Their partial pressures are 3, 1.5, and 4. What is the total pressure? Take a second. Add them up, and I get 8.5. Okay. All right. They're not all going to be addition. Sometimes they're going to be subtraction. Let's look at an example there. A balloon contains mostly helium and a little methane. The partial pressure of helium is 101.2 kilopascals. The total pressure inside the balloon is 101.3. Remember, that is my PT. That is my total pressure. Okay? Remember, PT equals P1 plus P2. And if there's a P3, you'd add P3. So, in this case, I'm using Dalton's law of partial pressure. Okay? That's an ugly 2, but we can see it. This is my total pressure. So this goes here. Okay? This is the partial pressure of helium. What is that missing piece? 101.2 plus what equals 101.3? Well, how do I get that? I subtract. That missing piece is 0.1 kilopascals methane. All right. Another take, a little different take. So this relates, how does the number of moles relate to the pressure? And the identity of the particle doesn't matter. All that matters is how many there are. Okay? And that's going to be important. So what is the partial pressure of carbon dioxide in a container that holds 5 moles of CO2, 3 moles of nitrogen, 1 mole of hydrogen, and has a total pressure of 1.05? So all of that pressure is caused from those 3 gases. What fraction of that is carbon dioxide? Well, it says 5 moles is carbon dioxide. 5 out of what? 5 out of 9. How do I know that? It says 5 moles carbon dioxide, 3 moles nitrogen, 1 mole hydrogen. So 5 out of 9 moles is carbon dioxide. So 5/9 of that total pressure, 1.05, is carbon dioxide. And when I take 5/9, 5 divided by 9 times 1.05, I get 0.58. I'm going to say 0.583 for sig figs. Okay? That would be the partial pressure that is caused from carbon dioxide. It's the fraction of the total that is carbon dioxide, dependent on how many moles there are. There are other ways to do this. This is probably the most easiest. The way I also show here is I figure out what fraction is the pressure of 1 mole. So because this total pressure is caused by 9 moles, I divide it by 9, and that's the pressure of, this is the pressure of 1 mole. Okay? How many moles are carbon dioxide? I'd multiply that by 5. And there's my partial pressure of carbon dioxide. So we're looking at how do individual components affect the total. All right, last example. PV equals nRT here, so it's going to be kind of adding last unit to our last week's lesson to this week's. Here I have a mixture of 2 moles of hydrogen, 3 moles of ammonia, 4 moles of carbon dioxide, and 5 moles of nitrogen. They're in a 45-liter container at 77 Kelvin. What will the resulting pressure be? So let's first answer that before we look at partial pressure. So here I need my variables. Looks like the first variable I have is moles. How many moles do I have? If I'm looking for the total pressure, it would be from all of my moles, 14 of them. The volume is 45 liters. My temperature is 77 kelvins. I'm looking for P. So I have the variables that I need to solve using PV equals nRT. I rearrange that equation. And I plug in and solve for P. I want to solve for atmospheres here. That's what I typically like to work in. So my R is going to be 0.08206. And I plug it all in. I get a pressure of 1.97 ATMs. Okay. So that's my total pressure. Well, what fraction of that total is carbon dioxide? Well, it says 4 moles carbon dioxide. Okay. So 4 out of 14. So I could take 4/14 times this to get the fraction of carbon dioxide, or I could divide that by 14 and multiply by 4. Either way, I'm figuring out what fraction of the total is from carbon dioxide, which is another way of getting my partial pressure. Okay? All right. So with that, we're going to jump right into this week's homework, and we're going to do a lot of these problems together. I'm going to assign a few for you. Okay? So let's read through this and do it together. Blast furnaces give off many unpleasant and unhealthy gases. If the total air pressure is 0.99 atmospheres, the partial pressure of carbon dioxide is 0.05, the partial pressure of hydrogen sulfide is 0.02, what is the pressure of the air remaining? So here I'm finding that missing piece. So why don't you take a second and try to solve. So again, my total pressure is 0.99. My partial pressure of carbon dioxide is 0.05. My partial pressure of hydrogen sulfide is 0.02. What is that missing piece? So how do I get that missing piece? Subtract. And I get 0.92 ATMs. Okay? That's number 1. I'm going to have you do number 2. We're going to go to number 3. If I place 3 moles of nitrogen, 4 moles of oxygen in a 35-liter container at 25 degrees Celsius, what will the pressure in ATMs be of the mixture? So here, what variables am I given? It doesn't look like I can just add them up here. It's a little trickier than that. And I'm going to give you a clue, and then I'm going to have you solve. If I place 3 moles of nitrogen, 4 moles of oxygen, 35 liters, and a temperature of 25, I'm looking for pressure. So what variables am I given? Looks like moles, volume, and temperature. What can I use? Ideal gas law. PV equals nRT. Remember to turn your temperature to kelvins. I'm looking for pressure. Okay? So I'm going to give you this. You can go ahead and solve. Okay? Why did I pick that R again? Because my pressure, I'm looking for it in atmospheres. All right? All right. Number 4. What's the partial pressure of carbon dioxide in a container that holds 5 moles of carbon dioxide, 3 moles of nitrogen, 1 mole of hydrogen, and has a total pressure of 1.05 ATMs? So here again, I'm looking at that fraction piece. What fraction of my total pressure 1.05 is carbon dioxide? 5 out of 9. Okay. There's my answer. All right. Number 5. I'm just going to talk about it a little bit, but you're going to answer it. A container with 2 gases, helium and argon, is 30% helium. And calculate the partial pressure of helium and argon if the total pressure inside the container is 4. So it says 30% by volume is helium. Remember, the identity of the particle doesn't matter. So to figure out that pressure of helium, I would just need to figure out 30% of 4. Okay? And if I figure out the partial pressure of helium, from that, use Dalton's law to get the partial pressure of argon. So I'm going to leave that for you. All right. Number 6, last one we're going to do together. 2 flasks at the same temperature are joined by a glass tube with a stopcock. A stopcock is a valve that you can open and close. So I'm keeping these 2 gases separate, okay, gas A and gas B, and I can open it up and allow them to diffuse or mix together. Okay, flask A is 4 liters and has a pressure of 2 atmospheres. Now this is not drawn to scale because flask B is 10 liters. Now this should be drawn a lot bigger, okay, but I just pulled a picture off the internet. This is the best I could find. But again, this one's going to be a little bit bigger. Okay? But anyway, doesn't matter. All right, so here is my pressure and volume of flask A. Here is my pressure and volume of flask B. What is the final pressure when I open up that valve and allow A to mix with B? Okay? All right. So, for this one, we're going to go back to earlier in this unit, Boyle's Law. Now, if you don't remember Boyle's Law, it looks like that. Okay? I know my initial pressure. I know my initial volume. I don't know my final pressure. Why? Because the volume is changing. If I open up this valve, what is my new volume? Well, it's just like if I have 2 separate rooms, okay? I have room A, okay? And room B, okay? So here's room B, okay? Room A and ugly room A and room B, okay? They each have their own volume. What if I knock down this wall, okay? I only have 1 room now. So what's the new volume? It's simply both of them added together. So here I have container A, container B. My initial volume is 4 liters. My final volume is 14. So I can use that to calculate my final pressure. Why can't I just add these 2 up? Because the volume is changing. Therefore, my pressure is going to change. So I can't just add those partial pressures up like we have been to get my total pressure because the volume is changing when I open up that valve. So I use Boyle's Law to find my new pressure of gas A. Okay, and that's nitrogen. Gas B containing carbon monoxide, I'm going to do the same thing using Boyle's Law. Okay, P1 times V1 equals P2 times V2, but here is my P1 right here. V1 is here. What's my new volume? Again, 14 liters. So I'm going to figure out that new pressure of gas B. Now, what is my total pressure? It's simply them both added together. So my total pressure, now that I've figured out my new pressures of each gas, nitrogen and carbon monoxide, I simply add them up to get my now total pressure. These are a little more challenging problems, but I'm going to assign one of them for you to do, and the last one is a little more challenging, but that's going to kind of be that extra one. Remember, if you're going for an A here, you do the assigned problems. Okay? If you're going for an A+, you want to, raise your grade even more, you can do those above and beyond problems, and that's going to be the problem 8 that I'm going to talk about in just a minute. So there's a lot of examples from this week's homework. I'm only assigning a few problems, and I'll talk about those in just a second. So hopefully that gave you a basic understanding of Dalton's law of partial pressure. Our homework, worksheet 8.4. Please do number 2. Finish number 3. Number 5, I think we did 4 together. Number 7, okay. And that extra above and beyond problem, number 8. Try that one for your challenge. So number 2, number 3, number 5, number 7, that's 4 problems. And that above and beyond problem, number 8. Okay? Basically try to finish worksheet 8.5. All right? That's this week's lesson. See you soon.